Hello everyone, this is Mrs. Lindsay. Today we're going to talk a little bit more. We're going to add on to reflections, translation, symmetry, a lot of that good information. And we are currently in the back to the beginning of the book, the Tannenbaum. So we are on chapter 11 in that book. Okay, so with this, there's examples for sure in this, but there's a lot of just kind of vocab and different things of that nature. So if you do want to actually kind of, excuse me, read through the notes first and then come back and go through the video, that might be a good idea. Basically, there are definitely a lot of things in terms of symmetry, an intuitive approach and formal. We're going to talk about a couple differences here with bilateral and rotational symmetry. So we'll start off with an example, bilateral. So you can kind of see with this, with the bilateral, if you just drew a line right down this Taj Mahal, the left side, you could fold it right over and it would map right onto that right side. So that's what we would call bilateral. Then we also have rotational symmetry. So again, as we rotate this, you can kind of see these are kind of these maybe leaves or stems. This is kind of the key component right in here. So as I rotate that, it's going to be the exact same thing with the sand dollar. Okay, so those are bilateral and rotational symmetry. Okay. Symmetries of a triangle. Okay, we're going to come back to this. This is actually an example, but we'll eventually come back to this. But we're just going to open up some questions here. The figure shows three triangles. And A is a scalene triangle. Again, all sides are different. In the middle there, B is isosceles triangle, so we have legs AB and AC are congruent, as well as the base angles B and C would also be congruent. Then we also have an equilateral triangle, the last one here. All sides are congruent, all angles are congruent. So again, a little review from before. In terms of symmetry, how do these triangles differ? Which one is the most symmetric? Which one is the least symmetric? I want you to kind of think about that. Like I said, we're going to kind of keep talking about it, but we'll come back to the answers a little bit later on these. So again, let's think about it. Hopefully, as we even just kind of were describing it, most people would answer that equilateral triangle, C, is the most symmetric, and scalene is probably the least. Is it correct, though? Why? What do you think about that? Okay, so again, we're going to come back to that. Okay, we could say symmetry is a property of an object that looks the same to an observer standing at different vantage points. Okay, we might think of symmetry in terms of ways that we can move an object so that when all the moving is done, the object looks exactly as it did before. We might follow the second approach a little bit more in terms of rigid motions. Okay, rigid motion, the act of taking an object and moving it from some starting position to some ending position without altering its shape, is called a rigid motion. Okay, sometimes isometry. We'll just really refer to it as rigid motion. If in the process, the moving of the object, we stretch it, tear it, generally alter its shape in any way, it is not rigid. Super important. It can't change the object, basically. Since a rigid motion, the size and shape of the object are not altered, distances between points are observed. Okay, so let's take a look here. If you look at these two examples, A and B here, on the left-hand side is rigid, on the right-hand side is not rigid. You can see the smiley face is not, it's not necessarily distorted, but it's not the same as the original. Okay, so again, everything needs to be the same in terms of those motions there. And the distance between any 2 points, so they highlighted the eyes here. So the distance between those x and the x prime is not changed, right? So and the distance between x and x prime would be the same as the distance between y and y prime, which is not going to be the case over here. These distances are going to be different. Okay, So in B, it says both position and shape have changed. At A, the motion does not change the shape. It only changed the position. Okay, so again, that's kind of a nice summary of what the rigid motion there would be. In defining rigid motions, we only are concerned with the net effect of the motion, where the object started and where the object ended. So where it started and where it ended. For example, rotating the happy face below 180 degrees has the same effect as rotating it 900 degrees. But again, we just look at the starting and the ending. We don't care about what happens in the middle. Okay? This implies that a rigid motion is completely defined by the starting and ending positions of the object being moved. Thus, two rigid motions that move an object from the same starting point to the same ending points will be called equivalent rigid motions. So the example we just saw would be equivalent rigid motions. A rigid motion of the plane, let's call it M, moves each point in the plane from its starting position P to an ending position P prime, also in the plane. We will call that point P prime the image of P. You could either say P prime or the image of P under the rigid motion M, and describes this informally by saying that M moves from P to P prime or P to the image of P. I'm okay with either way how you say that. That would be fine. We will also use the convention that the image point has the same label as the original point, but with a prime symbol added next to it. So again, P to P prime, not P to X prime, for example. It may happen that a point P is moved back to itself under M, in which case we call P a fixed point. So again, if that original point does not actually move after the motion occurs, it's a fixed point. All right, so what do we have? Again, this is an extension of what we did, what we ended with the last unit on, the last section on. Every rigid motion in a plane is equivalent to one of these: a reflection, a rotation, a translation, a glide reflection. These four types of rigid motions are called the basic rigid motions of a plane. And again, we're going to focus mostly here on reflections and rotations. A reflection in the plane is a rigid motion that moves an object into a new position that is a mirror image of the starting position. Mirror image is kind of a nice little way to sum that up. In 2 dimensions, the mirror is a line called the axis of reflection. From a purely geometric point of view, a reflection can be defined by showing how it moves a generic point P in the plane. All right, so let's again kind of take a look at these in terms of a geometric standpoint. The image of any point P is found by drawing a line through P perpendicular to the axis L and finding the point on the opposite side that is the same distance. So this blue and red line connecting P to P prime is really the perpendicular bisector. And this is your axis of reflection. That's what L is. So when I reflect P over L, I come up with P prime. So this distance in blue here is the same as the distance in red. So again, it doesn't matter if it's vertically, straight up and down, horizontally, however it is. Again, this is really a perpendicular bisector. And again, that's a good way to kind of think about that. But the distance, that perpendicular distance from P to the axis of reflection, and again, from the axis of reflection to P prime, should be identical here. Those are going to be equal. Points on the axis itself are what we call fixed points. So again, this is an example where P reflects onto itself, P prime. So again, that's what we call a fixed point. Some more examples here. Here's looking at a triangle. So the following figures show 3 cases, so we'll have a couple more here, of a reflection of a triangle ABC, so the blue triangle on the left, In all cases, the original triangle in blue is reflected to A prime, B prime, C prime. So sorry, my dog saw somebody walking by. So again, we're taking the blue, reflecting it onto the red. In this figure, the axis reflection L does not intersect the triangle. Okay, so and again, you can see these distances are preserved here. So if I'm referring to, let me go back, this distance here is the same as that distance along the perpendicular bisector. And it's that same way between A and A prime, C and C prime. Okay. In this figure, the axis of reflection L cuts through the triangle ABC. Here the points where L intersects the triangle are fixed points of the triangle. So again, these points right on this line, they would be fixed. We normally focus on the vertices, but again, since the original triangle, blue triangle, goes over the axis of reflection, then we're going to have some fixed points there. In this figure, the reflection triangle A prime, B prime, C prime falls on top of the original triangle because the axis of symmetry cuts through that vertex. So this is probably an isosceles triangle. That's what it appears to be. Again, we don't usually assume that. But the vertex B is a fixed point on the triangle, but the vertices A and C swap positions. So if you notice over here, they're again swapping positions under this reflection. All right, some properties here of some reflections. Property 1, if we know the axis of reflection, we can find the image of any point P under the reflection by making a point perpendicular to the axis through P and find the point on the other side of the axis that is equidistant. Thus, a reflection is completely determined by its axis L, the axis of reflection. So again, you're talking about the perpendicular bisector there. 2, if we know a point P and its image P under the reflection, and assuming P prime is different than P, we can find that axis of reflection L. It is the perpendicular bisector of P prime. Again, so super important that that is always the perpendicular bisector there. 3, fixed points of reflection are all the points on the axis of reflection L. Property 4, reflections are improper rigid motions, meaning that they change the left, right, and clockwise, counterclockwise orientations of objects. This property is the reason a left-hand reflection in a mirror looks like a right hand, and the hands of a clock mirror and a mirror are counterclockwise. So that's kind of a nice little description there of how looking through a mirror, again, a left hand turns to right hand, that type of thing. And the last one, if P prime is the image of P under reflection, then P double prime equals P. The image of the image is the original point. Okay, thus when we apply the same reflection twice, every point ends up at its original position. Okay. Identity. Okay, identity, what does that mean? A rigid motion that is equivalent to not moving the object at all. Okay, so again, it's the original object. So at first it may seem somewhat silly to call the identity motion a motion. After all, nothing moves, but there's a very good mathematical reason to do so. And here's why. Example, if we apply a reflection 2 times in succession and the result that all points move back to the original position, a reflection followed by itself results in the identity motion. So again, some properties of reflection. A reflection is completely determined by its axis of reflection L. A reflection is completely determined by a single point image pair. A reflection has infinitely many fixed points, all lighting on the axis of reflection, which we call L. A reflection is an improper rigid motion, and when the same reflection is applied twice, we get the identity motion. Okay, so again, that was kind of diving into reflections there. Now we're going to dive a little bit more into rotations. Okay, informally, what is a rotation? A rotation in a plane is a rigid motion that pivots or swings an object around a fixed point O. A rotation is defined by two pieces of information. First, the rotocenter, the point O that acts as the center of the rotation. Two, the angle of rotation, and that's actually the measure of the angle indicating the amount of rotation. In addition, it is necessary to specify the direction, counterclockwise or clockwise associated. Okay, so let's take a look at an example here. So this figure, so again, we're starting with P and we map it into P prime, all right? Geometrically shows how a clockwise rotation with rotocenter, O, and a rotation of alpha degrees, we don't know what that is, moves from P to point P. So again, it's got your rotocenter, it's got the degree, and it tells the direction. So in this case, clockwise. Those are kind of the three components of a rotation. All right, let's take some examples here of rotations of triangles like we did with the reflections there. So here again we have the original triangle in blue, ABC, and it's going to be reflected onto the red triangle, A prime, B prime, C prime, and that's again red. O is the rotocenter, lies outside of the triangle, and now we are rotating it clockwise 90 degrees. And you can see how they're kind of describing it over here. We're kind of moving it from a 12 o'clock to a 3 o'clock position. Okay. Here's another example. Again, the blue is the original. The red is the image. So this is kind of the upside down turn because we're doing 180 degrees. Now, notice it doesn't say if it's clockwise or counterclockwise because it doesn't matter. It's the exact same thing. If I do 180 degrees clockwise or 180 counterclockwise, you end up with this exact same image. So in this case, they are showing 180 degrees clockwise, but again, it's you don't necessarily have to specify that in this case. Here we have the rotocenter. In this case is, oh, I meant to highlight that before. Now that again, the rotocenter is inside the triangle, and in this case it is here as well. And this one we're doing a 360 rotation, and again, it doesn't matter if you say it's clockwise or counterclockwise, so it'll end up with the same. That moves every point back to its original position. So again, you can kind of really think of that as its identity. Okay. And again, we have some properties here of rotations. Okay, property 1, 360 rotation is equivalent to a 0 degree rotation, and that's known as the identity. Okay, so again, kind of going a full circle around. From property 1, we see that all rotations can be described using the angle of rotation between 0 and 360. For angles larger than 360, we divide the angle by 360 and just use the remainder. So in other words, a clockwise rotation of 759 degrees is equivalent to a clockwise rotation of 39. So if you take out all the 360s from there, if I just keep subtracting that, right? So I'm going to make this 6, 5, 9. And then again, I take out another one. You'll see what's left over. I keep going until I get a number between 0 and 360, and that's what it's equivalent to. So again, I just kind of keep taking that out. I did subtraction over here, but you can also do the division. But if you keep taking out that 360, it comes up the same way because, again, division is just repeated subtraction. So, in addition, we can describe a rotation using clockwise or counterclockwise orientations. So, taking this example from above, a clockwise rotation of 39 degrees is equivalent to a counterclockwise rotation of 321. Okay. Property 2, an object is rotated the left, right, and clockwise and counterclockwise, a little tongue-tied there, orientations are preserved. So a rotated left hand remains a left hand, and the hands of a rotated clock still move in the clockwise direction. Any motion that preserves the left, right, and the clockwise, counterclockwise orientation is known as proper. So again, a little bit different from reflections here, where this was actually not the case, right? A left hand went to a right hand. It was a mirror image of each other, not the same with a rotation. Note, a common misconception is to confuse a 180-degree rotation with a reflection, but they are very different. A reflection is an improper bridge motion where a 180-degree rotation is proper. So again, think about the mirror image. So left and right switch, we're 180 degrees, that the left hand stays and remains the left hand. Number 3, in every rotation, the rotocenter is a fixed point, and except for the case of the identity, where all points are fixed points, it is the only fixed point, which again is different than a reflection. And the last property here. Unlike a reflection, a rotation cannot be determined by a single point image pair. So that's kind of a good point to highlight there. Cannot do that by just looking at a single point image pair, P and P prime. It takes a second point image pair, Q and Q prime, to nail down the rotation. Okay, so if you take a look here at the diagram, we look at P, P prime. We need another point because, again, we can see that if I chose this bottom point as the rotocenter, I still have equal distance there. Okay, but again, if I move that up, I can also still have equal distance. So we need another set of pairs of points to figure out which one it specifically is. Okay. The reason is that there's infinitely many rotations that can move P to P prime. Any point located on this perpendicular bisector of the segment P prime, right? So if I draw this in, so any point located on that perpendicular bisector can be a rotocenter. So there's actually more options than just these two that are highlighted. Given a second pair of points Q and Q prime, we can identify the rotocenter O as the point where the perpendicular bisectors, so this perpendicular bisector of P, P prime, and the perpendicular bisector of Q, Q prime intersect. So that, again, will help us narrow down and determine where that rotocenter is. Okay, and then once we have identified the rotocenter O, the angle of rotation theta is given by the measure of angle P, 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 O, P prime, which is here. Or you could also say, and I'm going to highlight this a little bit more down here, Q, O, Q prime. So those should be equal. Properties of rotations, again, still kind of not new ones, but just kind of adding some notes here, right? In the special case where P, P prime and Q, Q prime happen to be have the same perpendicular bisector, the rotocenter O is the intersection of P, Q and P prime, Q prime. So in other words, you find the perpendicular bisector. Oops. You find the perpendicular bisector, which is that, happens to be the same of P, P prime and Q, Q prime. And then you just draw a line through PQ, draw a line through P prime, Q prime until it intersects. And then that would be your rotocenter. Okay, properties of rotations. A 360 rotation is equivalent to the identity, which is 0. A rotation is a proper rigid motion. A rotation that is not the identity motion has only one fixed point, and that's the rotocenter. A rotation is completely determined by 2 point image pairs P prime and Q prime, Q prime. All right, so now we're going to move on to symmetry for the last portion here of chapter 11 and identify different types of symmetry that we have. All right, so symmetry. Symmetry of an object or shape is any rigid motion that moves the object back onto itself. Okay. Example. What are the possible rigid motions that move the square in figure below back onto itself? So hopefully, so in other words, think about what lines can I draw on there when it's reflected over the line would result back onto itself. And hopefully you're kind of thinking about some of these lines. Just drawing one right in between kind of the top and the bottom, A, B, and D, C, which also then would work horizontally. But then also connecting basically the diagonals. So if again I rotate this, so if I just pick out one, I'm looking here at AC, this L4. If I take this portion of the square and I reflect it over L4, it lands exactly on ABC. Okay. So again, that's an axis of reflection. The square falls back onto itself. Now notice it does interchange points. So what it's talking about here in this example, it's talking about the line L1. So if I reflect, let me change colors here. So if I reflect this portion of the square over, points A and B are going to interchange places. Points C and D are going to interchange places. Okay. So that's what it's referring to. But again, the image is exactly the same. All right. Square also has rotation symmetries as well. Using the center, rotocenter O, we can rotate that by 90 degrees. So it can either be 90 degrees, 180, 270. Again, 360 is going to be basically the identity. Again, that's 0 degrees, but again, it rotates. But again, it's switching places. So if we just talked about the 90 degree one, so think about all these would move one position over if they did a 90 degrees. So A would take B's place, B would take C, C would take D, D would take A. Okay. All in all, we have easily found 8 symmetries, 4 rotational and 4 reflections for a square. Okay. Can there be more? What if we combine one of the reflections with the rotations? Is symmetry combined with another symmetry? After all, has to be itself a symmetry. It turns out that the 8 symmetries we listed are all there are. No matter how we combine them, we always end up with just these 8. So suppose that we let R90, R180, R270, and R360. So that's a little bit of a notation there. So the first one is rotation. This R90 is rotation by 90 degrees. Obviously, the next one is R180, so that's a rotation by 180. So this is kind of a little shorthand of how we write those rotations there. Okay. Then L1, L2, L3, L4, so again, referring to that diagram previously, are the reflections across the lines, L1, L2, L3, L4, respectively. So we're going to describe the motion obtained by doing L1 by R180. So we're going to actually do 2 of these motions and see what happens with that. Okay, so we're going to do L1 first, followed by R1. Let's go back. Go back here. So here's our square. This is the rotational. Here's the reflection. So the first one we're going to do, L1, so that's the vertical one. So we're starting out with our square as A over here, B, C, D. So we'll do that one first, and then we'll apply this rotation of 180 degrees. So hopefully you have a little more space than I do, but I'm going to squeeze this up on the top here. So I'm going to first draw the original square here. So that's going to be A, B, C, D. And I'm going to first apply the symmetry L1. So again, that was the vertical. And that would give me, again, a square. But now I have just A takes the place of B, B takes the place of C, etc. Just keep moving that along. Okay. Let me even switch colors again. Now I'm going to do R180. So that is, again, rotating D all the way over. D would go all the way over, and take the place of B. So D goes 180 over here to B. A goes 180 over to C. B goes 180 over to B. And C goes over here. So again, this is again doing a reflection and a rotation. And again, it still preserves our exact same thing, but what is it actually equivalent to? If we look back, it is exactly the same as doing L3. So A, B, C, D, if you take a look back, probably a little easier for you to take a look at that. But if I do that with L3, just in the original, A would take the place of D, B would take the place of C, they would flip-flop. So you can see that just doing two of them together resulted in L3. Okay, so let's try another one. Let's reverse it. Let's do, again, our original triangle, A, B, C, D. Let's do the rotation first. So again, A switches to C. B switches all the way over here to D. All right. C takes A, D takes B. And then we'll do, I can switch colors again. L1. So L1 again is the vertical. So again, the left and the right side are switching places. So now we get D here. C goes here. B, A. And what is that equivalent to? Yep, sure is. Same as L3 because we get the exact same thing that we got up there. Okay. All right, I'd like you to pause the video. I want you to try to do this third one here. So again, starting with your original A, B, C, D. First apply rotation of 90, then apply rotation of 180, and then push play when you're ready to check your answer. All right, so hopefully you got that to be our 270. Again, 90-degree rotation first, and then I did the 180. Which resulted in the original R270 rotation. Okay, so now let's take a look at a propeller here. Let's consider the symmetries of a shape shown. It's a two-dimensional version of a boat propeller or a ceiling fan with 4 blades. Okay. Again, we have a shape with 4 reflection symmetries. You can draw those 4 lines, basically very similar to the square, the vertical, horizontal lines, as well as kind of think about them being diagonally cutting through those blades there. Then we also have a 90-degree symmetry here. So every time we add the 90, 90, 180, 270, 360, we get the rotational symmetries as well. The last 2 examples illustrate an important point. 2 different looking objects can have exactly the same set of symmetries. We will say that 2 objects or shapes are of the same symmetry type if they have exactly the same set of symmetries. Here are the symmetry types, and this is an important little slide here. How we actually designate those. D sub n. This is the symmetry types of shapes with both rotation and reflection symmetries. The subscript n denotes the number of reflection symmetries, which is always equal to the number of rotational symmetries. So we would have said in our last 2 examples that we had D sub 4. Z sub n is the symmetry type of shapes with rotation only. Okay, so here we have both. Here we have rotation only. The subscript n denotes the number of just rotation symmetries. D infinity is the symmetry type of a circle and of a circular object such as rings and washers, the only possible 2-dimensional shapes or objects when the infinite number of rotations and reflections. All right, so objects, more examples of objects with the same symmetries here. So the symmetry type for the square, the propeller, each of the objects shown below would be D sub 4. So again, 4 reflections and 4 rotations. So hopefully you can see those. All those would be, again, horizontal, vertical, kind of the diagonal. And then again, they'd all have 90, 180, 270, 360, every single one of these. Okay. Snowflake has 6 reflection symmetries and 6 rotational symmetries. So this would be D sub 6. And again, if you want to think about it, try to figure out what those are. So hopefully 1, 2, 3. But then you also have the horizontal 4. Okay, so we're missing 2 more. What would those be? Hopefully you can kind of see that it would be right in between those as well. Ken always wants to do that on me. And then the rotation, kind of an easy way to think about it here. Sometimes when you see kind of these little pillars, there's 1, 2, 3, 4, 5, 6 of them. If I just take 360 and divide it by 6, it's going to be every time I do 60 degrees, I add 60 degrees. So you're talking 60, 120, 180, ... So that gives you all the way up to 240, 300, 360. So there's again 3 of them. So you just keep adding 60 degrees each time. All right, more about D sub n. We have seen the symmetry type of the squared is called D sub 4. Again, shorthand for 4 reflections, 4 rotations. More generally, any regular polygon, again, regular means all the sides are congruent, all the angles are congruent, with n vertices have n reflection symmetries and n rotational symmetries. So any regular polygon with n vertices has symmetry type D sub n. Okay. All right, let's change our propeller just a little bit. Slightly different. Okay. But does the symmetry point of view, is there a difference? Is it significant? Okay, or is it still going to be D sub 4? All right, we still have 4 rotational symmetries. Every single time we rotate it 90 degrees, it will be exactly the same. However, there will not be any reflections, because here's what happened. Just because, and let's go back to this diagram, you can see that these shapes are just slightly, yes, the same. But then when we go to draw our vertical line, so to speak, because they're slightly off, the blue then maps upon the red. So because they're a little oblong, again, it does not have any reflection ones. So this is Z sub 4 because it only has rotational symmetry. Okay. So shapes with rotations, but no reflections. So here's a couple other examples. The flower on the left has symmetry as Z sub 5. Hopefully that makes sense. It's got 5 petals. Then we're talking about jet turbine blades here, and there's 24 of them, so it's Z sub 24. And now we're going to go back to the propeller. So now you can see the top and the bottom blades are the same. The ones on the right and left. So how does that modify any reflection or rotation symmetries at all that we have? Well, still doesn't have reflections, but now it does change the rotations. Okay, 90 degrees won't work either because this top one is different than the one on the right. We have to match the top one to the bottom one. So that is now going to give it symmetries of 180 and 360 only. So this is an example of Z sub 2. Okay. All right, so more examples here with Z sub 2, 180 and 360. So the letter S, the letter Z, and you can see the card there, the Queen of Spades. Okay. And let's look at a couple other different ones here, other different examples of some of these D1s, Z1s, that type of thing. Symmetry of D1. One of the most common symmetry types occurring in nature is that of objects having a single reflection symmetry plus a single rotational symmetry. Basically the identities. That's D sub 1. Okay. Notice it does not matter if the axis of reflection is vertical, horizontal, or slanted, in basically all 3 cases here. It's still D sub 1. So it has 1 reflection and 1 rotation, which they are symmetry, the identities. Now, if we look at a Z sub 1, again, this is just rotation, no reflection. Okay, many objects have this as well. Many objects and shapes are informally considered to have no symmetry at all, but it's a little misleading since every object has at least the identity symmetry. So objects who only are symmetry is their identity is said to be, again, Z sub 1. So again, this is just the 360 that they have, or the 0 degrees. Then again, we have objects with lots of symmetry. Okay, so we've looked at these examples before. Very different snowflakes, but from symmetry point of view, they are, again, the same, but they're highly symmetric. Again, this figure shows a decorative ceramic plate. It has 9 reflection symmetries, 9 rotational symmetries, so it'd be D sub 9. You can see there's a lot of different examples of these out there. This one obviously gets a lot more complicated. D sub 32 on this one. And again, another example with several, D sub 36. All right, now let's take a look at D sub infinity. All right, are there two-dimensional objects with infinitely many symmetries? And the answer is yes, circles. The circle has infinitely many reflection symmetries. Any line passing through the center of the circle can serve as an axis. The circle also has infinitely many rotation symmetries. Use the center of the circle as a rotocenter, and any angle will work. Again, this is called D sub infinity. Now let's go back to the equilateral triangle. Okay, equilateral triangle ABC has symmetry of D sub 3, so 3 rotations and 3 reflections. So here are the 3 reflections. Let's think about what would it be for the rotations. Well, with our rotations here, if you want to think about it, I got to move this vertice to here and then move it here. So again, I'm really kind of thinking about 360 divided by 3 gives me 120. So every time I add 120, so then I get 240, then I get 360. Here are the 3 rotational symmetries. Okay, but again, you have 1, 2, 3 reflections, and 1, 2, 3 rotational ones. Okay, so this just kind of wraps up or summarizes what I was talking about with the reflections, L1, L2, L3. I think I actually labeled them slightly different than that. So they said L1 is the line A to the midpoint of BC. I didn't put A, B, and C on there, but that's what they're referring to, those lines right on there. Okay. And then again, this is talking about the 3 rotations of the 120 degrees, which is about the center. And the center in this case, hopefully you realize, would be right here. That's the rotocenter. Okay. So again, just summarizing. All right, so we can claim 6 are in all. Using the notation L1 times R20 to represent the rotation followed by reflection. Again, we can just kind of, this is again what we're talking about, what we did with the square there. You can just keep recording these and doing these as many times as you want, and then multiple ones, and they come right back onto just basically it's just either an R120 or an L1 or an L2, just even if you do multiplications of them. Okay. So again, R360 brings the triangle back to its original starting point, so that's the identity. And then the reflection followed by itself takes it right back to the starting point. So again, here's some more of these multiplication ones. If you do an L1 and L1, it's really just a rotation of 360. Same idea here. So a reflection is its own inverse. And you can see what it's doing with these. 2 rotations of 120 gives you just a rotation of 240. So they're just going through a lot of different multiplication ones. Again, like we did with the example with the square, I'm just not actually doing those out for you. Just really showing you again that there are 3 reflections and 3 rotations, no matter what you comprise of the different ones. Okay, but again, you can do this to continue to build all the combination of the symmetries. I'm not necessarily asking you to do that, but that is something that you can do. Okay. So this wraps up chapter 11, mathematics of symmetry, really again focusing on reflections, rotations, and then symmetry.